Hello, and welcome to the Rolls Battery Engineering Training webinar series. Today, we are going to talk about tips and tricks when using Schneider products, both their charge controllers and their inverters with Rolls flooded lead acid batteries. Just to note that this covers our flooded lead acid lines, the Series 4000s, 4500, Series 5000 batteries specifically. If you use these settings with our valve regulated batteries, such as the AGM batteries or the gel batteries, you could cause damage to the batteries by having too aggressive charge settings, too aggressive absorption time settings. So in the future, I'll be publishing the same type of PowerPoint presentation based on the valve regulated batteries. My name is Steve Higgins. I am the Technical Services Manager for Rolls Battery Company, or Surrett Battery Company, basically the same company. My contact information at steve@surrett.com. Here's my phone number if you feel like to call me. The best way to get a hold of me is via email. These are generally 30 to 40 minutes in length. This will probably be closer to 25 to 30 minutes in length. It's a little shorter, so hopefully you have time to sit and watch the whole thing, especially if you're watching this on YouTube. I have muted everybody's microphone so we don't get echoes. We have as clear a sound quality as we possibly can. If you have questions, you can use the text field. If you don't have access to the chat pane, or you are watching this on YouTube, you can send me an email at steve@surrett.com and I'll respond to you directly. If you like this webinar, or if you have problems with this webinar or questions, again, please feel free to post comments below, or you can send me an email directly at steve@surrett.com. Thank you. All materials are available for download. I have this webinar. I have many others. I also have PowerPoint presentations in PDF format. I have some sizing stuff. I have generally a spec sheet, things like that I share on Google Drive. If you want access to that, please send me an email, steve@surrett.com. I'll also send you a link to the YouTube site, and I'll put you on my list for our email list for when we do live webinars. Okay, so what we're going to talk about today is we're going to talk about system settings and programming for systems based upon a pretty common sized battery bank with some existing products that are out there that are manufactured by Schneider. Basically, what we're going to talk about the 16 S550 batteries. Those batteries they're 428 amp hour batteries, the C20 rate. We're talking about 2 parallel strings, so you have 8 batteries in the series with 2 strings of 8 in series parallel. So that's going to be your battery bank, basically about 41, 42 kilowatt hours of available storage. The array will be roughly about a 6,000 watt solar array connected to 2 MPPT 60 charge controllers. And then we have the XW plus 6848 inverter. We're also going to talk a little about the Schneider battery monitor kit. Some of the things we're going to specifically address: what are your minimum and maximum charging currents? What are your minimum and maximum charging or discharging currents? Your charging voltages, your absorption times, estimated peak solar production in different times of the year. We're also going to talk about average charging current from the inverter chargers and the other chargers, what you would normally see and what your peaks are. So to go on, so minimum and maximum charging currents. With flooded lead acid batteries, the minimum charging current, especially for a solar application, considering you're going to see roughly between 2 and 5 hours of really true charging every day, especially if we're talking specifically for a solar system. At a minimum, you really want, for a full-time off-grid system, about 10% of the C20 rate, which means if it's a 856 amp hour battery, we're looking at 85 to 90 amps of current minimum. And the reason for that is this: your absorption time. This is the absorption time formula. Basically, 0.42 is the assumption, or the knowing, that when you're in absorption, you're going to lose about 60% of this current. And so what that does is that allows us to kind of have a, for the lack of a better term, a best guess of where your current's going to be on average throughout the entire absorption time. You multiply that by 856, which is the amp hour capacity of the battery, divided by the nominal charge rate, and that'll give you roughly your absorption time. Ballpark, this is numbers within about 10 to 15% of where it's going to be. Winter or summer, depending on weather, it's going to vary. Your maximum charging current is 20%. The problem with lead acid batteries, one of the issues with lead acid batteries, is they have a higher internal resistance than, say, a valve-regulated lead acid battery. So they don't accept current as well as a valve-regulated, like an AGM battery or gel, which means if you were to run more than 170 amps of current into this battery, the battery could get hot, and that temperature is going to increase. It's going to specifically, especially under charging, is going to specifically be on the positive plate or the positive post. And what can happen is if you run too much current into this battery, especially during the bulk stage where it will accept that current, what will happen is it'll cause positive post expansion, and that positive post will typically, due to that heat, will rise out of the battery. If you ever walked into a battery room and looked at batteries, you could see batteries that have been over temperatured. Often they'll swell. And the other thing that you'll see is the positive post will actually be higher than the negative post. That indicates that the battery is seeing a lot of higher temperatures, and usually it's due to overcharging, and or especially if this battery is installed in a generator room or in a hot environment, you're going to see positive post expansion. So you want to so typically for this battery bank, we want to have a minimum single source charger of 86 amps to a maximum single source charger of 172 amps. You want to try to prevent from overcharging it. Minimum and maximum discharge currents. With solar applications, we tend to try to size these systems for a C20 discharge rate. What that means is for the two parallel strings of S550s, a single parallel string would be 21.4 amps. Two parallel strings is going to be 42.8 amps of current. Okay, so so if we exceed 42 amps of current, what that means is our battery bank becomes smaller. Now, if we take that 42 amps of current, let's just round it up to 43, multiply that 48, that's 2,000 watts. Divide that by 240 volts. That's 8.6 amps AC of current. So 42 amps DC equates to about 9 amps of current AC. So it's not a whole lot of load. So what happens is that you install the system, you drive away, your client adds more loads. So what ends up happening is your current goes up and up and up and up. So if your client is loading your system, if they're discharging at the C5 rate, if they're just discharging at the 5-hour rate, what that means is now they've only got 2.5 hours of backup time from a full state of charge, when you told them they would have 10 hours of backup time. So what that'll do is that'll cause problems, cause excessive generator run times. They're charging all the time. They're using a lot of extra water. Basically what happens is it causes customers to complain. Ideally, you want to educate your clients, or if you're an end user, you want to educate yourself about how much current is actually running when you're loading. And so what you want to do is you want to try to keep your currents in this range from that 42 amps and lower, or in this case, the 21 amps and lower. And what will happen is if you stay in this range, your batteries are actually going to stay at a higher state of charge over a longer period of time, which means they're going to last longer. You're going to have a lot healthier life for the batteries. They're going to be a lot easier to charge, and you're going to have less problems with sulfation. You might use a little more water because you're charging a little better, but the batteries are going to last longer. Estimated peak solar production. This is one of my favorite questions in the whole wide world, other than how much solar do I need on an application. I just did a training a couple weeks ago in Jamaica, in Kingston, Jamaica, and one of the people at the training, one of the trainees, said, oh, well, we're in Jamaica. We get 12 hours or 10 to 12 hours of sun every single day. Well, you may get 10, 12 hours of light, but your solar panels aren't seeing 10 to 12 hours of sun. And the reason that you're not seeing 10 to 12 hours of sun is because there's a relationship to the angle of the panels to the sun. You want to keep the panels within 30 degrees of your peak production. And so what sometimes people do is they'll have a daytime or a morning and an afternoon angle on multiple charge controllers to try to offset that. So if you're in Jamaica, you know, your average production is going to be 4.5 to 5.5 hours in the summertime. It's going to be 2 to 4 hours in the wintertime. If you're in the Pacific Northwest, you're talking 1 to 2 hours in the wintertime, and you're talking probably 3 to 4 hours in the summertime. You know, if you're in Yellowknife, Canada, then you're talking, you know, maybe a half hour to an hour in the wintertime and 3 to 5 hours in the summertime. So it varies depending on where you're at. It varies depending on the time of the year. So it's a good idea when you're sizing these systems to look at those quarterly numbers and to give your customer, to look at those numbers and give your customer a good approximation of how often they're going to have to run their generator during the off seasons when they're not producing as much solar. So on this particular system, we're going to talk about charge controllers first, because I like to set charge controllers up first. Bulk absorption, assuming that you're using temperature compensation. Temperature compensation on these systems is very important. And the reason it's very important is that when you charge batteries, there's going to be a natural rise in internal temperatures of the batteries. The natural rise of the internal temperatures of the batteries is going, if you're not adjusting your charging voltages properly, it's going to affect the overall life of the batteries. Okay, so regardless if you're installing the batteries in Hawaii, Harare, Zimbabwe, Lagos, Nigeria, Chicago, Illinois, Seattle, Washington, Barrie, Ontario, Vancouver, British Columbia, no matter where you're installing these batteries, you should always have a battery temp sensor installed on the system. That battery temp sensor should be installed on the side of the battery, about halfway down the side of the battery, below the level of the plates, and it should be installed in the hottest location, the hottest battery in the bank. So basically somewhere in the middle of the bank, not the edges, not the outside. It should be installed on the inside. If it's installed with double-sided sticky tape, you should run some duct tape or some electrical tape around the battery to make sure the sensor stays on the battery. Because often I go to these sites, it's either installed on the top of the battery, which is just picking up the air temperature between the air and the electrolyte, or it's installed on the post, and there can be a 20-degree temperature swing between the post and the side of the battery. So it's very important to have temperature compensation installed in these, regardless of where you are, because again, temperatures are going to rise and fall depending on the charging mode of the batteries. What these temp sensors do is they adjust the charging voltage based on the actual temperature of the battery. And so for flooded lead acid batteries, that's 5 millivolts per degree C per cell. And so on a 48 volt system, you multiply that 5 millivolts by 24 cells. That gives you 120 millivolts. So for every degree Celsius hotter, the battery voltage is going to go 120 millivolts lower. For every degree Celsius cooler, your battery voltage is going to be 120 millivolts higher. Okay, so if you've got a 10-degree swing positive, you're going to lower your voltage by 1.2 volts. If you've got a 10-degree swing negative, you're going to raise your charging voltage by 1.2 volts. That's how important it is. If you're not using battery temperature compensation, you're never properly charging the batteries. If you're never properly charging the batteries according to the temperature of the batteries, why should a battery manufacturer cover it under warranty? Something to think about. Anyways, so on our batteries, on Rolls batteries, flooded lead acid batteries, we want, for a solar application, we want the charging voltage to be between 2.45 volts per cell and 2.5 volts per cell at 25 degrees C. Now, that varies depending on how hard you're cycling the battery. The harder you're working the battery, the higher that voltage needs to be. So if this is a light use cabin, I'm going to have my voltage probably 57.8 to 58.8 to maybe 59.4. In this particular case, this is a full-time use cabin. So what I'm going to do is I'm going to set my charging voltage at 60 volts on my charge controllers. Okay. Again, temperature compensation is going to regulate that voltage plus and minus depending on what the actual temperature of the batteries is. Okay. Next thing is my absorption time. Absorption time is very important. When you start charging your batteries and your batteries get to that 60 volts, they're only really about 80% state of charge. So it's going to take time for that current to flow into the batteries. And that's what's called absorption time. And so one of the issues with absorption time is that current falls off fairly quickly because the battery voltage is fairly high. So you've got to take into account that fall off in current. If you just assume that you're going to charge at 90 amps, you got 2 hours or you got 200 amp hours to go, then the problem with that is you're going to get too short of a time. The batteries are never going to be fully charged, and you're going to have problems with them a year and a half, 2 years down the road. Okay, so what we have is we have this absorption time formula. That's 0.42 multiplied by the C20 rate divided by nominal current in bulk. Okay, and so the 0.42 is the assumption that you're going to lose roughly 50 to 60% of your overall charge current during the absorption time. Okay, the 856 is the C20 rate of the batteries, and the 90 amps here is my average nominal current that I'm expecting to see during that stage. So what that means is that, I mean, 6,000 watts of solar, your peak's going to be roughly about 120 amps of current. Are you going to get 120 amps of current nominally? Probably not. Panel temperature, battery temperature, system temperature, insulation values, how much sun you're actually getting on the solar panels, that's going to affect how much actual current that you see on average. So I've derated it a bit. So I'm going to use 90 amps here. So this means 0.42 multiplied by 856 divided by 90. My absorption time is going to be roughly 4 hours. That's how I'm going to set my absorption time on my charge controller. We've talked about battery temperature compensation. That's going to be 120 millivolts per degree Celsius. It comes defaulted at 108 millivolts per degree C. You need to make sure you adjust that. If you don't adjust that, you're not properly charging your batteries. And then last but not least, we have the battery capacity. I'll get into this in a little bit, but for the Schneider product, we want this set at roughly 1 to 1.5% of the C20 rate. So I'm going to want this to be roughly about 12 to 13 amps. That's going to help determine your state of charge metering and make sure your state of charge meterings are properly being hit. Again, you may need to adjust these voltages and these settings based on the time of year. In the summertime, you're going to have less consumption, but you're going to have higher production. So you may have to lower your set points a little bit. In the wintertime, you're going to see more consumption and lower production. So you may need to raise your set points depending on what you're on. So you want to, on average, an off-grid, a full-time off-grid cabin, you're going to have to adjust your set points typically once in the spring and once in the fall. Maybe one more time depending on how bad the weather gets or what your specific gravity readings are coming through. I'll address some of those concerns a little later. So now on the Schneider beam, or the battery monitor kit, something how it works. Basically what the Schneider product does is that when you program the battery capacity, so if you program the battery bank capacity at 856 amp hours, what it does is it takes 2% of that number. Okay, so roughly 16, 17 amps, 17, 18 amps of current. When the current going into the batteries drops below that 18 amps of current for 1 minute or 1 second, or however, I'm not even sure how long the delay is, but I know probably a minute or two delay. When the current drops below, going into the batteries, drops below that number, the state of charge meter on the Schneider battery capacity, battery meter, thinks the batteries are 100% state of charge. The problem is that's not really the way the battery companies want. We want to see the current go below that setting for at least 60 minutes. Okay, so when you go below the end amps or return amps for at least a 60-minute time period, that is when the batteries are really truly full. They're not really accepting any more current. So we're looking for that 60-minute time frame. So what you do, instead of setting your battery capacity at 856, okay, what I'm going to do is I'm going to set my battery capacity at 600. And what that's going to do is that will set up a 12 amp return amp setting on the state of charge meter. So what we'll do is when your current goes below 12 amps, so you've got a 6 amp difference. And so basically sitting at about a little bit lower battery capacity lowers your return amp setting, which encourages the charger to stay a little longer, which encourages the batteries to become fully charged before your meter actually says it's 100%. Now this varies from system to system or user to user. Sometimes you have to tweak this. And so what I would suggest you do is the first 4, 5, 6 months of the system, once a week you take a look, or once a month, or once every 4 to 6 weeks, you take a look at it at the end of that charge rate, and you make sure that the battery capacity, the battery specific gravities read that 1265 to 1275 good range. That would indicate that, yeah, your settings are perfect. If your specific gravities are a little higher, maybe you need to raise that number. If the specific gravities are a little lower, you might need to adjust that number a little lower to compensate. So now onto the inverter. So we set the charge controllers at 60 volts. What I'm going to do with the inverter is I'm going to set the inverter voltage at 59.6. What this does is this prioritizes the solar over the inverter. So if for some reason you go 4 or 5, 6 days without decent sun and the batteries are low, the generator starts. Generator starts, 7, 8 o'clock in the morning. It starts to run. Sun comes up. Now you're getting generator charge and solar. Well, what will happen is if you leave the generator alone, what you should do is leave it alone and let it finish. That way, what happens is the solar can finish out the charge. The solar will take it up to 60 volts. The inverter will shut off at 59.6 for the absorption time. And what will happen is the inverter will get the batteries into that 90 percentile scale while the charge controllers finishes off the battery charge. And that way, by the end of that first day, your batteries are back to a full state of charge after sitting for a week at a low state of charge. So that helps prioritize the generator, and it helps prioritize the solar, over the generator. Absorption timer, again, same thing as I did before on the solar. The XW6848 can do 140 amps of current, okay? Is it going to be charging at 140 amps of current? Probably not, okay? So I'm going to derate that a little bit and call it 110. So that gives me an absorption time of 3.26 hours. So 3 hours and 10, 3 hours and 15 minutes, maybe 3 hours and 20 minutes. So you set that up. Again, battery temperature is 120 millivolts. And then battery capacity, I would set my battery capacity at sorry about that, at 600 amp hours. And what that'll do is that will set my end amps roughly about 12 to 13 amps, and that'll ensure that my state of charge meters are accurate from day one. If you have a problem, say you set this incorrectly to start with, you set it too high and your batteries have become sulfated, what you need to do is you drop your battery capacity lower to lower that number to make sure that the state of charge meters don't reset to 100%. If you do that, then what will happen is your batteries will have a higher overall capacity. It will eventually come back. Some people will set that to 0. Some people will set it to 100 amp hours in an attempt to try to recover lost battery capacity. So at this point, if you're done programming your inverters, you're done programming your charge controllers, you operate the system, you never have to check it again, right? Everything's perfect. It will self-adjust, and the inverter's smart. It'll self-adjust and fix everything for you, right? Well, that's a big wrong. It will not. So you need to go back to it and check it. So on a brand new installation, I'm going to check every 2, 3, 4 weeks just to see where my full charge is getting. I'm going to check my numbers just to make sure that I'm getting to a full charge on a relatively common basis. The harder you cycle the battery bank, the more often it needs a full battery charge. Okay. If you're working the battery bank 15, 20, 30% every single day. It wants to see a full 100% recharge at least once every 7 to 10 days, preferably 7 days. If you're, say this is a weekender cabin and you're not working it very hard, you don't have to have as much of a charge. You can extend that for every 2 to 3 weeks. And so you want to look at that and see, you want to look at those numbers every once in a while and see how you're charging and compare how you're charging versus how you're discharging. Again, the harder you work it, the more often it wants to see a full 100% charge. The lighter you work it, the less often. Typically, it's about 1 to 4 weeks. I typically like to get into the full state of charge every 1 to 3 weeks at the minimum. It's going to keep the batteries healthier longer. So 2 weeks later, 3 weeks later, you call the customer, hey, Joe, how's your system going? What are your specific gravities coming back? And he sends you back this chart. It's 225, 230, 225, 230. So they're all coming in a little lower. So what's happening here? Well, what's happening here is basically you're undercharging, or your client is loading the batteries heavier than expected. And that's actually really common in this business. Is clients will promise one thing, and the next thing you know, they're loading the batteries heavier than what the installer expected. Now there's a little bit of a squabble. So what you're going to do to fix this is, one, you can adjust the charge settings. You can adjust the absorption time. You can adjust float voltages. You can adjust float times. You can make slight changes to your settings. Wait a couple of weeks, see what happens. If you continually get low specific gravities, then something else is going on. Something's not properly charging the batteries. You may have to go back out. Maybe a breaker trip. Maybe you got a wire that's shorting out, or you got a GFCI that's tripping on a PV array, arc fault problem. It could be one of 100 things, and so you may need to go back out and take a look at it and see what's going on. If your client comes back to you with this, you see 290s, 1300s, 1310s, 1320s. Technically, here what you're doing is you're overcharging. Doesn't happen very often, but it can. So what you want to do in this case is you want to lower your settings for a little bit. Drop your voltages 0.2 or 0.4 of a volt. Basically, what's happening here is you're overcharging. Your client's not using it as hard as you expected, and so you want to make adjustments. If you leave your specific gravities at this high of an acidic content for a long period of time, you're going to cause damage to those batteries, and those batteries are going to fail prematurely, regardless of who makes them. If they're regardless of who makes the specific battery. So, okay, at this point in time, we don't have any questions. At least I don't see any. If you do have any questions, or you're watching this on YouTube, please feel free to send me. You can either put feedback below on the buttons below, or you can email me directly at steve@surrett.com. I'd be more than happy to help you out. Again, thank you very much for listening. I appreciate your time. And again, if you have any questions, feel free to ask those questions. Have a nice day. Thank you very much.